Hello everyone, I hope you're doing well. In this video, we'll use the variational method to estimate the energies of one-dimensional harmonic oscillator in the first excited state. So all in all, what we are going to do in this video is to find out the energies for the first excited state of a one-dimensional harmonic oscillator by using the variational method. Okay, so you must be wondering that where is the video for the ground state of the harmonic oscillator using the variational method. So it's already uploaded. I'll link that video in the description box as well as in the comment section where I'll pin that comment. Okay, so you can easily check it out, and let's quickly get started for the first excited state of one-dimensional harmonic oscillator and how we are gonna calculate this energy state as well as its wave function using the variational method. Okay, now to begin with the solution, there are two things that we have to do in first place to proceed the solution. And the first thing, we should know the former states of the oscillator. Okay, for example, here we want to calculate the first excited state, so we should know what was the ground state wave function. Okay, or what were the assumptions related to ground state trial function or the exact function. So you should know what the ground state wave function was. Okay, because it is the aspect of using variational method that the later states depends on the former states. Okay, if you want to calculate, for example, the second excited state, so you should know what the first and the ground state wave function were. Okay, the previous states guides the later states in variational method. That is why the first thing that you should keep in mind to proceed with the solution is what was the ground state wave function. Let me write it here, and even you can use in this form. Okay, that's acceptable. That is the trial wave function that we used in the first video where we calculated the ground state wave function for the 1D harmonic oscillator. Okay, so you can use it in this form, or you can use the exact form that is actually this. Don't get confused. I'm just making your way clear because that's how you are going to use this method. Whenever you are about to calculate the higher states, you should know what the lower states were. Okay, you should have a knowledge about the lower states because they will guide you to devise a perfect trial wave function. Okay, so this information will help you to devise a trial wave function for the first excited state. These are the initial steps and they will guide the whole process. Okay, these are the basis of the solution. Devising a trial wave function is the most important step in the solution. It will guide your whole solution later on. Okay, so these are the two critical steps. The first step is already done. We know the ground wave function, that is this. Okay, you can use this form or this. I'm gonna use this one because it is less complex and it contains the essence of the solution. So I'm gonna use this one. And the second step is to devise a trial wave function for the first excited state. Okay, and for that purpose, what you should keep in mind is that here I'm gonna mention the rough things, and what you are supposed to write in the paper will be written here in a neat form. So stay tuned. Don't be scared if you see, because I wanna make sure that you understand things. It's not necessary that you will get the same problem in the exam. I just want to develop your understanding and make you intellectually developed through this video. So that is the main purpose that I have in my mind while filming the videos. So devise a trial wave function. So if you watched the first video, you must have remembered the three things that I mentioned while devising the trial function for the ground state. The same things will guide us to devise a trial wave function for the first excited state of 1D harmonic oscillator. The first thing was that the wave function should be, if you see the ground state, it was an even function. You can see that it is an even function. If you replace x by minus x, okay, the wave function remains unchanged. If it is an even function for the ground state, then it will be an odd function for the next state in line. So the next state was the first excited state. So the first excited state should be an odd function. Okay, it's an even function here, so the next state will be an odd function, and the other state, like the second excited state, would be a even function, and so on. Okay, that is something that will continue to happen. So the wave function should be odd function. Okay, and to make it odd, what we will be doing is to multiply x with the exponential function. What should appear in here, we'll see it later on, and we'll multiply it with some b digit. B ensures that it is normalized wave function. Okay, it's a normalization constant, and it always appears in all of the trial functions for all of the cases that we have. Okay, so that is not something out of the out of the box, something special. Okay, so that is always there. Always multiply a normalization constant. Here we multiply a, here we multiplied b to make it different, that they are not same. So bx e to the power, now we'll have the same function in the power as well, and I'll justify why. So the wave function should be odd function. Okay, and other than that, it should have one node. In ground state, there was no node. You must remember that. There should be no nodes in a ground state, since it's the ground state, and the second state in line should have one node. Okay, and we'll confirm it, that whether it has one node or not. And what we mean by node is that it should be 0 at one place only. This wave function should be 0 at one place only. So that is what node means. If there are two nodes, it means the wave function is 0 at two different points, at two different values of x, and so on. Okay, if there are three nodes, it means there are three values of x, which makes the wave function 0. So that is what node means. Okay, and a point of least displacement from mean position in terms of waves. So that is the other thing that the wave function should have. And third, it should be defined at x approaches to infinity. It shouldn't become infinity at infinity. Okay, it should be defined at x approaches to infinity. That is the property of any analytical functions that we have out there, or any analytical wave functions. Wave functions should not approach infinity as x approaches to infinity. They should be well defined, in other words. So that is another situation that should be satisfied. Okay, so let's write these things down. This is the wave function that satisfies all of these conditions. I'm going to use beta here because the adjustment parameter could be different, and it should be differentiated from the ground states parameter. Okay, that is why I use different parameters here. That is equals to b x e to the power minus beta x squared. That is the trial wave function for the first excited state. And let me write down these things here, and then we'll confirm that how this satisfy all of these conditions. Okay, solution or calculation. We know that the ground state wave function for 1D harmonic oscillator has falling form. It's totally up to you if you want to write the exact one or whatever. That doesn't make any difference. It contains the essence of the original solution, and that's important. Now let us approximate the first excited state energy that we represent by sample E1 and its associated wave function that would be automatically calculated. The trial wave function, we always have to devise a trial wave function to begin with the variational method. Okay, so the first thing that we do is to devise a trial wave function. That's the thing to, as I told you earlier, for the first excited state, because that is something that we need to calculate. So the trial wave function would be for the first excited state psi 1, and it should be an odd function from orthogonality property, since psi naught was even function. That is why that this function is odd. It should be odd and should have one node, since psi naught has 0 nodes, and should be well behaved wave function. And one of the property that well behaved wave function is that they have some B normalization constant, B as normalization constant, and psi 1 should be defined at x approaches to infinity plus minus infinity. Okay, these are all things that we keep in mind while devising a trial wave function for the first excited state. Okay, and keeping these things in mind, we devised following trial wave function where x will be one of the variable, because wave functions depends upon the position parameter, and it will depend on another constant, that is adjustable parameter beta, that is introduced in variational method to account for the things that we don't have an idea about. Okay, because here we are making some guesses and there are obviously some properties and things related to the first excited state that we don't have an idea about. So we adjust those properties with this adjustable parameter beta. Okay, so it will account for the things that we didn't consider. So that is equals to b x e to the power minus beta x squared. Beta needs to be calculated, b needs to be calculated, and beta would be calculated later on, because that's something that we can't calculate right here. We'll calculate it later. But b is a normalization constant that we'll calculate first, and then we'll proceed with calculating the first excited state energy and then its wave function. So that is equation number 1. That is the trial wave function. 1 represents the trial wave function. Trial wave function for the first excited state of 1D harmonic oscillator. Alright, now let me justify that this wave function satisfies all of these conditions. Okay, so let me justify it, otherwise I can't sleep at night without justifying this to you people. Okay, the first thing, that it should be an odd function. Now the property of odd function is that psi 1 at positive x would be equals to negative psi 1 of negative x. That means if I replace x with minus x, it would be equals to negative of that quantity. So let's do that. I'm replacing x with negative x here. B into minus x e to the power minus beta it's x squared, so it's minus x whole squared. So minus will come here, b x e to the power minus b minus x whole square means b x squared again, because negative becomes positive when it's squared. And psi 1, here we had, you know, x now, so we can write minus x in place here because that is psi of minus x. Okay, this is psi 1 of minus x because we replaced x with minus x here, so this is psi of minus x, that is equals to minus bx e to the power minus beta x squared. Now what is this? This is psi 1 of positive x, so we can write it here. Minus is as it is psi 1 of x. Okay, and we can easily take this negative sign to the other side of the equation, and we can see if we write it here and positive here, so we can see that psi 1 of x is equals to negative of psi 1 of minus x. That is the condition for the odd function. Okay, in even functions they are exactly equal to each other, there is no negative sign as well, but in odd functions what happens is that the wave function gets reflected. Okay, so it's reflected like that, so it's negative of this wave function. So that is how we saw that this wave function is a odd function. Now what would happen that if we haven't added x squared here, it would have become neither odd nor even function, because the power would have become plus beta x, and taking negative sign common wouldn't make it sine 1 of x. You can confirm it. Okay, so in that case it would have become neither odd nor even function. That is why I included the squared power here to make it an odd function. Okay, so this property is done. Now it should have one node, which means that it should be 0 at one point only other than infinities. Okay, infinities are not included as some points. So this is the wave function, and putting it equals to 0. Now the exponential function is never equal to 0 other than infinity, so that doesn't count. B is constant, that doesn't count, so x could be equals to 0. And if x is 0, the wave function could be 0. If you put x equal to 0 here, the wave function becomes 0. And other than that, there is no other point that can make it equal to 0 other than infinity. Obviously, infinities are not included here. So only x is a point where it goes in 0. So that means it has only one node. Alright, and in case of ground state, we saw that we had only this exponential function, and putting it equals to 0 doesn't satisfy us other than infinity, so it doesn't have any node because it doesn't become 0 at any point other than infinity. That's it. That is the definition of a node, and it applies everywhere. So second condition satisfied. And what if we put x approaches to infinity into this psi 1 of x? Okay, let me use some different page. Psi 1 of x, if limit x approaches to infinity is applied on it, what would happen here is that this is the wave function, all right, and at extreme limits this factor dominates. Okay, here x doesn't matter. You must be wondering that if you put x infinity here, the whole function becomes infinity, but that is not the case when it's multiplied with the exponential function. That's the property and behaviors of exponential functions, that they become dominating at extreme limits. Extreme limits mean at extremely lower values and at extremely high values they become dominating. So if x approaches to infinity, then this exponential factor will determine what would be the value of this wave function. If we put infinity here, squared e to the power minus beta plus minus, because minus doesn't matter, as we saw that minus becomes plus, so it's infinity. Again, infinity into beta is infinity with negative sign. E to the power minus infinity is equals to 1 over e to the power infinity and e to the power infinity is infinity, 1 over infinity is 0, so the wave function becomes 0 as x approaches to plus minus infinity. That is how all of the conditions are satisfied by our magical trial wave function. That's so perfect. So 1 is a perfect trial wave function, and now we can proceed. Okay, now we can die peacefully after justifying it. Now let me write two different conditions that should be satisfied by this trial wave function. Now for a well-behaved wave function, there are two additional conditions that should be satisfied, and these conditions will help us later on in the video. You will see them, their application, or you can predict where we'll be using them. So the well-behaved wave functions should satisfy the normalization condition, the normalization and orthogonality condition. Okay, orthogonality condition, you can say. I advise you people to understand these two conditions because they are so much common in quantum mechanics that you'll see them everywhere. Okay, because all wave functions that you deal with should be normalized and orthogonal, and sometimes it's called as orthonormal when they are both normalized and orthogonal at the same time. So this is a really frequently used condition, and you'll see them in perturbation theory, in normal calculation methods, and whatever you will see. Okay, so we'll be using it here in variational method as well, so you can predict where we'll be using it. So let's first write the normalization condition, which says let us make a heading. That's a heading. You can use marker and psi. Since we are talking about the first excited state, that is why I'm gonna write it for the first excited state. The wave function, which is a function of x and beta here, you can see the trial wave function that we have devised. Its scalar product with itself, our whole space should be equals to 1. That is the normalization condition in ket-bra notation. Okay, that's the ket and that's the bra, and that's the ket-bra notation that shows the normalization condition, and we'll write them in integral form as well later. Okay, we are just writing it in ket-bra form here. So in normalization condition, what happens is that the self-scalar product of a wave function is always equals to 1. Okay, and the orthogonality condition says orthogonality condition, in orthogonality condition we have two different wave functions. So since we only know the ground state and first excited state, so we can write that the scalar product of a ground state with its excited state would be equal to 0. That's the orthogonality condition. Okay, orthogonality condition tells us that psi 1 and psi 0 are unique on their own and they are linearly independent of each other. Okay, so orthogonality conditions tells us about the uniqueness of the solution. Alright, so psi 0 will be unique to psi 1, and later states psi 2, psi 3, psi 4, they're all orthogonal to each other, which means they are linearly independent of each other. Okay, so that is the orthogonality condition and that's the normalization condition. So these are the two conditions that you have to mention because you'll be using them later on, and if you mention all of the important stuff first hand and then you proceed with the other things, then it will make your way clearer because now you know that what you have to play with. Okay, so we'll first find out normalization constant using normalization condition. If you guessed it, yes, it's right. After finding it out, we'll be calculating the energy for the first excited state, and then we'll automatically calculate the wave function for the first excited state. Here we go with the normalization constant, and we know that normalization condition is psi 1. Okay, I'm not using as a function of something like that. Okay, I'm just using it the way it is. And now let's convert it into integral form. And in integral form, what happens is that the integration happens over whole space, like from minus infinity to plus infinity. Then we have ket. Ket is written as it is. Then we have bra, and in bra section what we do is put steric over it to show that it's a complex conjugate of this wave function. And since we know that our wave function doesn't contain iota in it, that is why psi star will be equals to psi simply. And this integration will occur in a whole space, so it's dv equals 1. And we know that our wave function is one dimensional, that is why dv converts into dx. dv will become dx. Okay, so let's put the value of psi 1 here. Psi 1 is b x e to the power minus beta x square. Then we have psi 1 star, which is same because there is no iota involved in here. And yes, and then it's dv. In place of dv you write dx, that is equals to 1. Here b and b, they are constants, normalization constants, so we'll take them outside of this integration. It will become b squared, x and x becomes x squared e to the power minus. We have both exponential factors, so their powers will be added because their bases are same. Okay, their base is e, both of them have similar base. If we have similar bases, then the powers would be added, and the same thing happened here. B squared minus infinity to plus infinity x squared e to the power minus 2 beta x squared dx should be equals to 1. We are almost done here. We'll use the integration formula. Okay, I'll write here the general formula that will generate all the results for similar looking integrals, because they will be occurring later on in calculating the energy as well. Okay, so that formula should be remembered by you all people because it was used in ground state wave function and energy calculation. It is used in first energy calculation, and maybe we'll use in second energy calculation as well. So let me write the formula here. We know that this integration x to n, okay, e to the power minus 2 x squared. Okay, so there should be alpha as well. I'm using alpha just for differentiation. We'll replace it with beta when we'll be putting it. That should be equals to pi by 2 alpha. It's 2 alpha here, so 2 alpha will appear here. If it's 3 alpha here, 3 alpha will appear here. If it's 4 alpha, 4 alpha will appear here. Okay, so that's how the 2 alpha, they are married to each other. Then we have this multiplication sign where we keep on multiplying until this number is reached, divided by 4 alpha to the power n. Okay, that is the general formula, and whatever the case is, you will insert the values and you will get your desired, formula and its result. As we can see here that it's x square only, and if we put n equals to 1, 2 into 1 becomes 2, so it's x squared. The same formula will be generated here if we put n equals to 1. I hope you got it. As you can see, if you compare the powers, it's 2 are already there, so multiplying by 1, 2 into 1 will make it 2, so n should be 1 here. Okay, and if we put n equals to 1 here, what we will get is, let's say, x to e to the power minus 2 alpha x square dx, that will be equals to pi by 2 alpha. They will remain unchanged because there is no n involved here. Now here you will see that if you put n equals to 1 here in rough work, 2 into 1 minus 1, it's 2n minus 1, it's 2 minus 1, which is equals to 1. So our product will contain numbers up to 1, which is only 1. The later digits will not be included. This number shows that what is the last digit of this multiplication series. Okay, if it would have been 5, then you will stop at stop, you'll stop at 5. It will be 1, 3 and 5 only, but as you can see that only 1 is there, so 1 is the last digit to include, so it's the first digit as well, so it's 1 only here, divided by 4 alpha to the power 1. So we have got the result, which is pi by 2 alpha 1 over 4 alpha. That is the value of this thing. Now let's put this integral right there to find out the value of b square. I'm putting it here, pi by 2 alpha dot 1 over 4 alpha should be equals to 1, and we need b square, so we'll take these things on the other side. 4 alpha is divided here, so it will be multiplied here, and it's pi by 2 alpha, it will become 2 alpha by pi on the other side of the equation. And if this form of b square is really helpful when we will be putting it into the formula later on, so remember that form. I'll call it as equation number 2, but for the sake of a particular form that books mention about the value of b square, to get that form, let me tell you how you can do that. 4 alpha could be written as squared power 1 by 2, so that square and power cancels out and you will get 4 alpha as a result. So what I'm doing here is to combine all of these terms inside the square root. It's square root and it's square root. Taking square of 4 alpha becomes 16 alpha square, and it becomes 16 alpha square with power 1 by 2, which is I'm writing in the form of under root, and since this is under root as well, so they could be combined. It's 2 alpha by pi. 16 into 2 is 32. This is alpha square and this is alpha, it becomes alpha cube divided by pi under root. This is b square, and now it's b square. I want to calculate b, so I'll take another root, so it will become 32 alpha cube by pi. It was already 1 by 2, so taking another 1 by 2 makes it 1 by 4. Alright, this is the normalization constant for the first excited state wave function, you can say. Okay, and remember that form as well. We'll be putting it later on when we'll be calculating the energy. So that is the normalization constant, remember that. First excited state, we had trial function, trial wave function for the first excited state. Of 1D harmonic oscillator. And that is given out to be E1 E psi 1 as a function of x and beta. Beta is the adjustable parameter, and this whole function is equals to b into x e to the power minus alpha x square. We'll not put the value of b right here because it's an extra thing, because it's a constant. It doesn't bring any difference to the whole calculation. We'll put it at the end of the calculation. So that is the psi 1 of x. Now the expectation value of energy E1 is given by E1 as a function of adjustable parameter, because it depends upon adjustable parameter for now, and that should be equals to psi 1 Hamiltonian psi 1. Okay, since it's energy for the first excited state, that is why the wave function that will determine its value will be the wave function for the first excited state. It's psi 1 here and psi 1 here, and since we want to find out the expectation value of energy, that is why we'll have an operator, Hamiltonian operator, which is energy operator, to calculate the energy value. Okay, so let's put the value right here, And before doing that, we should know what the Hamiltonian is for the 1D harmonic oscillator. Let's call it as equation number 4. And here H Hamiltonian, that is equals to minus h cut square by 2m partial square by partial x square, or you can use d square by dx square. Since it's a 1D case, that is why we'll have d square by dx square only. We don't need to use other dimensions. Plus the this is the kinetic energy term, and then we have potential energy term, which is 1 over 2 m omega square x square. Okay, that is the Hamiltonian expression for the 1D harmonic oscillator. That is the kinetic energy term, and that is the potential energy term. Okay, now from 4, let's write them in integral form, and then we'll put the values. Integration minus infinity to infinity, and we'll have psi 1, this is in ket notation, that will appear as it is. Then we have h operator, then we have psi 1 again, and then we will have dx because it's 1D case. And here the order matters. H bar is a operator that will apply on something that is on its right hand side. This operator will apply on psi 1, and then it will be multiplied with psi 1 on the left side. Okay, so first we have to evaluate h bar into psi 1, and then we'll multiply with psi 1, and then we'll integrate it. Okay, so the order really matters here. Don't mix the order. Sometimes what happens is students write it like that. This is wrong. You can't write it like that. If it's originally like that, you write it in the same order, psi 1 first, then h prime, then psi 1. It's steric on it because it's in bra vector, but since psi 1 is originally a real function, it doesn't contain any complex quantity. That is why that doesn't make any difference. Let me put the values. Psi 1 here, this is bx e to the power minus beta x square, h prime minus h cut square. Okay, what I'm gonna do is to let minus h cut square by 2m to be equal to c, because you know, writing it again and again in the whole calculation is really hectic. And here 1 over 2 m omega square, I'm gonna write it like that. And it's also a choice if you know, let it equals to d, for example. That would be really helpful, because writing them again and again and again, it's really hectic. We'll put these values at the end of the video. I'm gonna let 1 over 2 m omega square to be equal to d, and c is minus h square by 2m. It will make the calculation way easier. So c, no negative sign, c partial square by partial x square plus dx squared, then we have psi 1 bx e to the power minus beta x square and dx. Now let's simplify this integral. Here b and this b, they are constants, so they will be multiplied with each other, and it's b square as a result. We can write b square outside of the integral. Now let me multiply this thing, x e to the power minus beta x square, with this quantity and this quantity. It's c partial square by partial x square, x e to the power minus beta x squared plus d x square, another x, this one, e to the power minus beta x square. Keep that in mind that this b has already been taken out side of the integral. So here this term needs to be calculated. Okay, this term, we have to find out the double derivative of this term, and I'm gonna calculate it separately, and we'll insert it back into the equation number 5. It's because we don't have to write all these terms again and again, okay, without any simplification. So let's calculate this term here. It's double derivative, so let's find out the first derivative. I have separated the derivative. this is the first term and this is the second term. We will use the product rule, and in product rule, first term as it is, derivative of second term, then second term as it is, derivative of first term. Partial x by partial x is 1, okay, and partial by partial x of exponential e to the power minus beta x square. Let's see what it is. That is equals to partial by partial x into x. Derivative of exponential is e to the power minus beta x square comes as it is, then the derivative of its power, which is minus beta x square, okay, plus e to the power minus beta x square. Since partial x by partial x was 1, so only e to the power minus beta x square is left behind. Let's do this. X e to the power minus beta x squared minus beta will come outside, and derivative of x squared is 2x plus e to the power minus beta x squared. Partial by partial x, it's minus 2 beta, this x and this x makes x squared, e to the power minus beta x squared plus e to the power minus beta x squared. There's one more thing that we can do, is to take e to the power minus beta x square as common, so that we'll have 2 beta x square plus 1 inside. So there are two terms, this is first term and this is second term, and we'll have to use product rule again because it's double derivative here. So e to the power minus beta x square as it is, derivative of minus 2 beta x square plus 1, then minus 2 beta x square plus 1 as it is, derivative of exponential term, e to the power minus beta x square. If we take derivative of these two terms inside, derivative of minus 2 beta x squared is minus 2 beta as it is, derivative of x squared is 2x, then plus derivative of 1 is 0, plus minus 2 beta x squared plus 1, derivative of e to the power minus beta x squared is minus 2 beta x. I hope you remember that. I'm writing it directly because we have already seen such case. Minus 4 beta x plus minus 2 beta x squared plus 1. Here we have e to the power minus beta x squared minus 2 beta x. We can see here that we can take this minus 2 beta common. Since it's a constant, so we can take minus 2 beta common. Let's see what's remain inside. So minus 2 beta is taken common, so it's 2x left behind here, e to the power minus 2 beta x square plus sign. This minus 2 beta whole quantity was taken outside, so it's x left behind, e to the power minus beta x square into minus 2 beta x square plus 1. Let's multiply it inside. 2x e to the power minus beta x square plus, let's multiply it, so it's minus 2 beta x square becomes x cube e to the power minus beta x square plus x e to the power minus beta x square, since it's 1 here, hence it will become minus 2 beta 2x e to the power minus beta x square minus 2 beta x cube e to the power minus beta x square plus x e to the power minus beta x square. That is the double derivative that we have calculated. I took minus 2 beta as common because that's a constant and it will be taken outside of the integration. That is why I did it. I didn't took anything else common because it will not make any difference. Okay, it will complicate it. So taking it in this form is the most sensible thing to do. Let's put it back into the equation number 5. Here we can see we'll put this value right back here, and c is already there, and we can see that this term is also multiplied with this quantity and this quantity. It's common to both of these. Okay, it will be now multiplied inside, and we'll simplify it, and after that simplification, after multiplying all these quantities with each other, we will integrate them. Okay, so let's put in 5 E1 of beta equals b squared. When we have such lengthy terms, be focused and double check everything that you write down, because a minor mistake can make your mind go mad. Because I made one mistake while calculating it, while I was solving it. I made one mistake and it took hours to recognize what mistake I made. So C, and then we have this whole term. It's minus 2 beta already, so I'm using minus here, 2 beta here. Bracket should be changed. Then bracket starts, this whole term will come. You can see C minus 2 beta is written with C, and then we have the other whole term, this one here, 2x e to the power minus beta x squared plus minus 2 beta x cube e to the power minus beta x squared plus x e to the power minus beta x squared, bracket close, curly bracket closed as well. This whole term has already been written now. Okay, then we have plus sign and this term, plus sign, and this thing is multiplied with this term, and this thing is multiplied with this term as well. So what I'm gonna do is write it separately with this term. Okay, because I have separated the brackets, so I'm writing this term here, reducing another step. Okay, and there is a need of one more bracket because integration is written single time, so it's dx closed. I hope you got it how I did that. Here we can see that this term was common to this and this term. I have separated this term and written it separately with this term and this term. I hope you people are not confused here. What I did here is that I wrote this thing because it's common to this term and this term. So I multiplied with the first term and with the second term as well, and written it here like that. Okay, it's with the first term, which is this, and it's with the second term as well, and enclosed in brackets, and the similar integration because I haven't separated the integration yet. Now let's continue with some simplification, and what I'm gonna do is to multiply this term inside of these terms. So I'll keep on taking minus 2bc, 2 beta c as common outside of the integral, and I'll multiply this term inside this term, okay, directly, and we'll separate this integration sign with b square with both of these terms. B square and integration sign is common to this term and this term, so it will separately appear with both of these terms. Okay, so in next step we'll separate the integration sign, and let's separate it first and then we'll continue. Then we have this term minus 2 beta c and 2x e to the power minus beta x squared minus 2 beta x cube e to the power minus beta x squared plus x e to the power minus beta x squared, bracket close, and dx, plus then we have b squared again because it's common to both of these terms, so it will appear here as well, integration sign and then this same thing, and let's multiply x here. It's d x square, x and x, it's x4 e to the power minus, it's e to the power minus beta x squared e to the power minus beta x squared, so it will become e to the power minus 2 beta x squared, powers will be added, dx. Next we'll multiply, it's b square, and then I'm taking minus 2 beta c outside of the integral, and now inside the integration we'll multiply x e to the power minus beta x squared, this thing, with all of these terms. Okay, and what I'm thinking is to separate the integration sign with each of these terms, so we'll be multiplying this integration and this term with each of these terms, so that we will get different integrals and we could perform the integration right away and the steps doesn't get elongated. So e to the power x e to the power minus beta x square multiplied with the first term, which is 2x e to the power minus beta x square. Then we have minus sign, since it's a minus sign here, and integration sign, and we are supposed to write dx here as well because integration is accompanied by its dx factor. Integration, then we have 2 beta x cube e to the power minus beta x square already there, and then this term, since all of the operations has been done, so that doesn't matter if I write it first and the other thing second or whatever order is followed or not, that doesn't matter when there are no operators involved, since we have already simplified and calculated all of the operators and applied all of the operators. So I have written this term first and then I'm writing this dx. So bracket closes plus b squared, then we have d, I'm taking d outside, when this is integration minus to plus infinity x4 e to the power minus beta x square dx, it's 2 beta x square dx. Now we'll take the constants outside of the integral, and after that we will simplify it. It's almost done. Minus 2 beta c b square, bigger bracket, integration, and we have this 2 that I am taking outside, integration, none of the other things are constant so they will not be taken outside. It's x and x squared e to the power minus 2 beta x squared, since there are two exponentials, dx, minus, it's 2 here, it's beta as well, so beta x cube, and it's x, so it's x4 e to the power minus 2 beta x square dx, plus there is no constant involved here, it's x squared e to the power minus beta x squared dx, then plus, bigger bracket close, plus b square d minus infinity to plus infinity x4 e to the power minus 2 beta x square dx. Alright, and you can see that we have a total of two different kinds of integrals here, one with power x square, the exponential remains the same, and the other one has the power x4 and the exponential remains the same, you can see here. Okay, so let's see what their values are depending upon the integration formula that I mentioned earlier when we were calculating the normalization constant. The same generating formula will be used here. It will generate you the result for these integrations. Okay, so let's see what it is. Let me write the general formula here, and we can call it as equation number, it's E1, we can call it as A. Okay, and we know that remembering such important integrations is really crucial. It will help you whenever you need them. Okay, so it's highly recommended that you remember these formulas. Minus 2 beta x square dx, this integration equals pi by 2 beta, that's always there irrespective of the value of n, and then we have 1 dot 3 dot 5 dot, and the last number in the series is determined by this factor which depends upon n divided by 4 beta power n. The value of n is determined from the integration that you want to calculate. For example, as you can see, it's x to the power 2, so 2n, you can equate both of these powers. 2n equals to, what would be the value of n then? N equals to 1, 2 cancels out, so it's n equals to 1 for this integration, and it's power 4 here, so 4 equals this power 2n, so what would be the value of n? We can take 2 to the other side, So it's to do the n equals 2. In one case it will be taken as n equals to 1, and in other case it will be n equals to 2, and depending upon that we can evaluate their values. So let's calculate it for n equals to 1. You can write it like that, and it's x to the power 2 e to the power minus 2 beta x squared dx. That should be equals to pi by 2 beta. And let's calculate what's 2n minus 1 for n equals to 1 in rough work, so that we may know where to stop. It tells you where to stop. It tells you the last digit of this series. So 2 into 1 minus 1, 2 1s are 2, minus 1, 2 minus 1 is 1. So it stops at 1, and this starts at 1 as well. So 1 is the only one number that you can write in this series, and divided by 4 beta to the power 1, which is again this thing. So we can write pi by 2 beta 1 by 4 beta. That's the value of this integration. And then we have for n equals to 2, x4 e to the power minus 2 beta x squared dx equals pi by 2 beta. And let's do this thing in rough work and see. It's 2 into 2 minus 1. 2 is already there, n is 2. 2 to the 4 minus 1 equals 3. So it's 3, 1.3. Since this thing tells you the last digit of this series that could be multiplied, we will continue to multiply until this number is reached. So the last digit is 3, so 1.3 would be included. 4 beta to the power 2 pi by 2 beta, 3 by 4 4 is 16 beta squared. Okay, let's plug these values right back into this equation. We are very near to our solution because we just need to simplify it and we'll get the result really quick. After that, cb squared bigger bracket 2, then we have this. I'm gonna write their values correspondingly by 4 beta first, and then under root pi by 2 beta minus 2 beta, it's already there, then its value, which is this, multiply by 3 by 16 beta squared under root pi by 2 beta plus, it has no coefficient, so it's simply this 1 by 4 beta pi by 2 beta bracket close. Then we have plus b squared d, then this, its value is this, 3 by 16 beta squared pi by 2 beta. Okay, that's it. Now what we have to do is to, okay, now we'll multiply this term inside and we'll simplify. Some of the things will cancel out and we'll put the value of b squared as well, and it will bring us to a really simple form. Okay, so let's do this. We'll multiply it inside, so it's minus 2 beta cb squared, this 2 by 4 beta under root pi by 2 beta, then this minus minus becomes plus, it's 2 beta, it's 2 beta here as well, as 4 beta squared, 3 as well cb squared divided by 16 beta squared under root pi by 2 beta, then this plus minus becomes minus, and it's 2 beta cb squared by 4 beta pi by 2 beta. Then we have this term that remains the same because 16 beta squared will cancel out things after putting the value. Okay, there are some cancellations that we can do right away. As we can see, this beta square and this beta square cancels out. This 4 and 16 cancel out. My nephew was crying. It's 4 ones are 4 and 4 fours are 16. So it's 4 left in the denominator. And here it's 3cb square by 4 that is left here after cancellation. And here we can see that this beta and its beta, that's cancel out. Its 2 2s are 4, 2 and 2, and this 4 cancels out, and it's cb squared that is left behind here. Here we can see that's beta, and this beta cancels out, and 2 1s are 2 and 2 2s are 4, so it's 2 that is left behind, cb squared by 2 here. So let's write them next, and we'll put the value of b square right now, the one that I told you people to remember, that we'll be inserting in here. So let's do that. Let's write these things down. It's minus cb square pi by 2 beta plus 3cb squared by 4 pi by 2 beta minus cb squared by 2 pi by 2 beta plus 3b squared d by 16 beta square pi by 2 beta. That's the energy so far. And as I told you that I'm gonna use this value of b square, which is equation number 2, because this will cancel out with pi by 2 beta, and it will be really helpful. And I don't know why I used alpha here. It's beta that we continued with, so it's beta actually. I don't know why I make such mistakes. Here I use beta, and why I'm using alpha here, just because I think I mentioned the formula in alpha form and I continued with alpha, so it's beta instead of alpha. And we'll be using equation number 2 as the value of b square to insert here, because it will simplify the things much more. And we have b square value to be 4 alpha 2 alpha, sorry, it's beta 2 beta by pi, that's only, minus c 4 beta under root 2 beta by pi. That's the value of b square, and pi by 2 beta is already there. 3c by 4, b square value is 4 beta under root 2 beta by pi by 2 beta, minus c by 2, b square value is 4 beta 2 beta by pi by 2 beta, 3d by 16 beta squared 4 beta pi by 2 beta by pi by 2 beta. Let's cancel out everything. So this cancels out, it's under root pi here, 2 beta cancels out, and this cancels out everywhere. Okay, now this 4 and 4 cancels out as well, and it's 2 here and it's 2 here, so it's 2 beta c that is left behind here. Let's continue writing them down. It's minus 4 beta c here, since everything else cancels out. It's 3c beta that is left behind, since all of the other things have been cancelled, and it's 2 beta c, everything else cancels out. And here let's see what remains. It's 4 4s are beta, one of the beta cancels, and it's 3d by 4 beta that is left behind. Now they will add up with each other because it's all beta c beta c beta c, so let's add them up. It's minus 4 plus 3 is minus 1, minus 4 minus 2 is minus 6, plus 3 is minus 3 c beta plus 3d by 4 beta. That is the energy so far. Now we can insert the value of c and d here. C, what was c and what was d? C was minus h squared by 2m, and d was 1 over 2 m omega squared. We can insert it here, minus 3 beta, and c is minus h squared by 2m plus 3 by 4 beta, and d, which is 1 over 2 m omega squared. minus minus becomes plus. This is 3 h cut square by 2m beta and plus 3 by 2 fours 8 m omega square 1 over beta. Okay, we have got the final form for the expectation value in terms of beta. Let me call it as equation number B. This is the expectation value that we have got so far for the first excited state, but you must be wondering that what is the value of beta. And that's the same question that variational principle answers, that what should be the value of beta that minimizes the error in E, or we can say that what is the most suitable value of beta that brings that approximated value of energy for 1D harmonic oscillator to the original value. For example, as you already know from the theory of variational method, that it's a approximation method. It doesn't guarantee you the exact solution, but it guarantees you to get the nearest possible solution to the original one. Okay, it guarantees you a solution that is very nearer to the original one, and it will be equal to the original one if the trial function or the trial wave function that you have guessed is the the perfect. So here, to assure that the expectation value that you are getting against the value of beta is the most accurate one, the variational method guides us to do this variation with respect to beta, and we'll put it equals to 0, and we'll find out the value of beta that makes this statement true, and that value of beta will be inserted back into this equation, and the energy that we get with that value of beta is the best possible energy that we can get out of the trial wave function that we have devised at first place. Okay, so let's do that. This thing means this is a variational principle. We can use the statement using variational principle now. If I summarize the steps that we have done so far, we first devised the trial wave function for the first excited state based on the prior states, that is the ground state. And secondly, what we did was to use the trial wave function to find out the normalization constant. After finding out the normalization constant, we calculated the expectation value of energy and we got to this result. Okay, and after getting to this result, we can see that the beta is here, and beta is some adjustable parameter that the variational principle has to tell us that what to put in here instead of beta to get a value for the expectation value, because it's something that is not specifically defined yet, so we have to define it. And the variational principle, because there are so many values of beta that we can insert in here, so what's the best possible value of beta that should be inserted here, and that brings this approximated energy value that we are working with to the closest original one for the 1D harmonic oscillator. And for that purpose, variational principle tells us to put its variation equals to 0 against beta and find out the value of beta that satisfies it. Okay, so let's do that. That value of beta will be inserted back into it, and the energy that we get after that will be the final result for the first excited state energy. Let's do that. It means that we'll take its derivative with respect to beta, whatever the adjustable parameter is. If it's alpha, you'll differentiate it with respect to alpha. If it's beta, you'll do it for this, and so on. So we'll put it equal to 0. Partial by partial beta 3h cut square by 2m. I highly recommend you people to watch the video that I did on this conceptual basis for variational principle. All of these questions will be addressed there, that why we do that, why and how, and everything is addressed in that video. And conceptual videos makes your way clearer and less ambiguous, so it's always recommended to do the conceptual part first and then do the problem part, then solve the problem. Partial by partial beta of beta 3m omega square by 8 partial by partial beta of 1 over beta 3h cut square by 2m. Partial beta by partial beta is 1 plus 3m omega square by 8 its derivative is minus 1 over beta square equal to 0. We'll take this to the other side of the equation. So it's 3m omega square by 8 minus 1 over beta square. It will be, it's added here, it will be subtracted here. This minus and minus sign cancels out. Okay, we need beta square and we'll take it here and they will be taken here. It's divided here, it will be multiplied here. It's multiplied here, it will be divided here. It's divided here, it will be multiplied here. So let's cancel out things. If they could be 3 cancels out, it's 2 and it's here. So m and m square omega square by 4 h cut square. What a perfect square that we have got. So what would be beta, you must be wondering. So it's beta equals m omega by 2 h cut after taking under root on both sides. So that's the value of beta, and let's call it as C. We'll put in B. E equals 3h cut square by 2m, value of beta, which is m omega by 2h cut, plus 3m omega square by 8, 1 by beta, which is m omega, and this 2h cut will appear here. Let's simplify. M cancels out, 1 of the h cut cancels out, and we have 3 h cut omega by 4. 3 by 4 h cut omega plus m cancels and 1 of the omega cancels, 2 4, and we have 3 h cut omega by 4 again. So it's 2 h cut omega by 2 times h cut omega 3 by 4. You must be confused. So 2 3 h cut omega by 4. Okay, that is what I'm saying. Since they are the same term, so they are 2 times this term. 2 and 2 cancels, so it's 3 h cut omega by 2. 3 by 2 h cut omega. That's the energy for the first excited state of 1D harmonic oscillator, and that's equal to the original value. Here we can see that this is the energy for the first excited state, and that is what we have got with our method as well. So we can confirm that the variational method and the trial wave function that we have used was the best one, and we did our best. So this is the first excited state energy. You can use the subscript E1 here. Since I was making the video in many fragments, that is why I just forgot to mention the subscript 1, but you can do that. As you are watching the video, you can see this thing only. In some places I just in normalization constant I wrote alpha instead of beta, and it was all because there is so much things happening in my house that distracts me, and that is the reason why these things happens. But I just figure them out later on and I just mention them, and these are minor mistakes, you know, writing one in the subscript, that's not a big deal. What's the value of beta? We'll use this value of b here, 32 beta cube by pi power 1 by 4. Okay, we'll write them in rough work so that we can put it back into the equation for the trial wave function, so that we can get the wave function for the first excited state. So this is the energy for the first excited state. Let's write something about it. This is the energy for the first. That is something that we have been saying for a long time before, but we need to mention it again so that people may know, your professor may know that you know that what you have got, and it is equals to the original value. Hence it has 0 adder, and that's the value of E1 that you have got against beta naught. Okay, and here we know that the trial wave function was psi 1 x and beta equals bx e to the power minus beta x squared. That is the trial wave function. The wave function for the first excited state, is obtained by putting beta equals beta naught, which is m omega by 2h cut. This is actually beta naught that we have got by putting this that expectation value equal to 0. That is why we called beta naught. So that's beta equals beta naught. Let's put that value right back into this form to get the wave function x beta naught. So it's b, value of b 32, beta naught here because we are taking beta naught 1 by 4 e to the power minus beta naught x squared. Let's put the value of beta naught here. Beta naught is m omega by 2h cut whole cube whole power 1 by 4 e to the power minus beta naught, which is m omega by 2h cut x squared. Let's simplify, and we are just about to get our wave function as well. M cube omega cube 2 cube is 8 h cut cube power 1 by 4 e to the power minus m omega by 2h cut x squared. 8 ones 8 4, so it's 4. One mistake that always I make, it's here x as well, it's x. So 4m cube omega cube by pi h cut cube whole power 1 by 4 x e to the power minus m omega by 2h cut x squared. That is the wave function for the first excited state. And okay, this is the wave function for the first excited state, and it is in full agreement with the exact expression. The wave function for the first excited state, and D and E are in exact agreement with the original, or you can say full agreement with the original or exact expressions. Okay, so that is how we have reached the end of this video finally, and in next video we'll be finding out the energy for the second excited state and its wave function for the 1D harmonic oscillator. Alright, so I hope you got it. I hope the video was clear enough for you to understand it seamlessly, because I believe that I have done a good job. Please tell me in the comment section, and let me know if you have any queries. I'll respond to it as quickly as possible. Till then, take care and goodbye. Let me go to my nephew and console him.